Hello, here's some more waves practice questions. We're starting here with state two properties shared by all electromagnetic waves, which distinguish them from all other waves. Right, I think this is how I started the last video. It shows how often this comes up, so I won't write it out again. Travel at speed of light, c equals 3 times 10 to the 8 meters per second in a vacuum, and they're oscillating electric and magnetic fields. I mean, this comes up a lot. Just see the previous video if you just want me to repeat the same thing that I've just said there. Two columns below list 4 regions of the electromagnetic spectrum and 4 orders of magnitude of wavelength in meters. Right, so draw a straight line from each one to each one. So microwaves, UV, gamma rays, infrared light, and we've got wavelength here. So the gamma rays, they're going to have the shortest wavelength. So that's going to be coming up here. Then next one down, we're going to have ultraviolet, it'll be the next shortest one. Then we're going to have infrared, and then our longest one is going to be the microwave. So this is just remembering the electromagnetic spectrum, really. I mean, it's certainly helped out by, if you know which way round the visible bit is going, that we've got the red part of the visible spectrum at the longer wavelength and the violet part at the shorter wavelength, and that certainly helps you get ultraviolet and infrared in the right place. So, but really, you're just having to remember the different parts of the spectrum on that. Right, part C, this looks like we're back onto standing waves again. So figure 8.1 shows a microwave receiver R placed between the microwave transmitter T and a flat metal sheet. Explain why R receives 2 signals of different amplitudes but of the same frequency. All right, so they've started with something slightly different then. So we're going to have that, right, so we're saying that R will receive, so R will receive is going to get the direct signal, so a direct wave, and a reflected wave. So that's 2 things. So that's why it's going to get the 2 signals. So that was the first thing that we had to say. And then we can say these will have the same frequency, but they're going to have different amplitudes because the reflected wave has traveled further. So reflected wave has traveled further, so we'll have a different amplitude, a lower amplitude. The reflected wave has traveled further, so we'll have lower amplitude. So there we go. It's a different start to what they normally have on these. Explain why the strength of the detected signal varies between maximum and minimum values as R is moved towards or away from the metal sheet. Right, this is really saying, this is the question of, well, how do we set up the standing wave? Where does it come from? So we'll be going through those usual steps again of saying that well, I suppose we can say slightly fewer steps here because we've already mentioned about the reflected wave. So we can say that the reflected wave superposes with the incident wave. So this is the usual part 2 of our description. I missed out the word with incident wave. That then forms our standing wave, creating standing wave with nodes and antinodes. Did they call it standing wave or stationary wave? I don't think they've actually used the term in this way, so I'm going to use standing wave this time. So yeah, with nodes, antinodes. So the usual sort of stuff that we have for how a standing wave is set up. Actually, we might need to say a little bit more than that, because they are saying about moving R towards or away from the metal sheet. So this means then that we're going to have a variation in signal strength between T and the sheet. Between T and sheet. Because then that explains what's then going on with R. Because otherwise we haven't actually said, we said there's a standing wave, but we haven't said why that would have any effect, why it would be picked up when you're moving R around. Why would that make any difference? So putting that in at the end just really bolsters that answer up a bit. Right, part 3, determine the wavelength of the microwaves given that the distance between adjacent positions of maximum and minimum signal strength is 7.5 millimeters. Right, so this is remembering with your standard waves, well, you don't even have to remember it necessarily. So say you've got a standing wave. So if we've got these, that's 3 nodes. So just thinking, okay, that was meant to go through that middle node. So if that looks like one wavelength, doesn't it? So if we're going from a node to an anti-node, adjacent ones, which is what they're saying here, going from minimum at the node to maximum at the anti-node, that is clearly a quarter of a wavelength. So the wavelength is going to be 4 times 7.5 millimeters. So that's what, 30 millimeters. So if you get stuck with the standing waves, just drawing them out, draw out a wavelength. Or if you know other things, like they're talking about a first harmonic or something like that, if you're in a closed tube or on a string, and that's our fundamental frequency, well, you can see that's half a wavelength once you've drawn it. It's just straightforward to see. So similarly, if you've got a tube closed at one end and open at the other, well, we know that is a quarter of a wavelength. You can just see it just by looking at it. So drawing the pictures is very useful when you're dealing with these standing waves. Right, the amplitude of the signal from transmitter is A. The amplitude of the 2 signals detected at R are 0.8A and 0.6A. The changes in amplitude of detected signals are negligible as R moves 7.5 millimeters. Okay, fine. Show that the ratio of the maximum intensity to the minimum intensity of detected signal is about 50. Right, the thing that you've got to be noticing here straight away is they've changed here, talking about amplitude, then they're talking about intensity. And we know that the intensity is proportional to the square of the amplitude. So we want to do the maximum. Let's start with the amplitude. So maximum amplitude that you're going to get is where we're adding these two together. So we're going to have 0.8 plus 0.6A. That's our maximum. Our minimum is going to be where you're subtracting them. So we'll have 0.8 minus 0.6A. So that's what we got there. But that's just for amplitudes. So we need to then square that in order to get the intensity ratio. So we can ignore all of these. We're going to say, well, that is 1.4 divided by 0.2, which is 7. That's our amplitude ratio. So our intensity ratio, so you could write this out again. I mean, I'm just running out of space. So what you'd want to do here is say, well, we've got 1.4 over 0.2 equals 7. So that would be the max amplitude over the minimum amplitude. Then you can say, therefore, max intensity over min intensity is equal to 7 squared, because the intensity is proportional to the amplitude squared. So, and then that's giving us about 50. Yeah, where we're getting our 49 for that. So yeah, work it all out once for the amplitude and then just square it up. And then you've got the thing there for intensity. Right, that's quite a nice question again. Well, I think we've only got one more to go on this one. Figure 5.1, the solid line on the graph represents the displacement y against position x of a progressive transverse wave on a stretched wire at time t equals 0. A dotted line shows the displacement later. Okay, right, so it started off at this solid line. It's moved in one direction or the other. I don't think, oh, it's moved to the right. So it's moved to the right. So we've got this direction of travel, and now this peak here has moved along to this peak here, is what it's saying. Determine the wavelength of the wave. Right, okay, well, we can just read that straight off of the graph. I mean, if we're going from 0 there, we're getting back to where we started there at 0.6. So that's 0.6 meters. So that was a nice easy starter there. Explain how figure 5.1 shows that the period of the wave is 1.5 milliseconds. So it told us something about time. Oh, here we go. So after that amount of time, so we can say, so for A part 2, we can say in 0.75 milliseconds, wave has moved, well, it's moved half the wavelength, isn't it? Has moved half a wavelength. So period equals 2 times 0.75, which equals 1.5 milliseconds, because that's the time it takes to move a whole wavelength. Calculate the speed of the wave along the wire. So the speed is, well, distance over time, velocity over period. So that is 0.6. I said velocity over period, didn't I? Distance over time, wavelength over period, 0.6 divided by, well, we just worked out the period, 1.3 times 10 to the minus 3. So 0.6 over 1.5 is, what's that, 0.4. So 0.4 times 10 to the 3, so that's 400 meters per second. Right, that was good. Part B, consider the oscillations of the wire at positions P and Q. Okay, yeah, they've marked on P and Q here in these two spots. See figure 5.1. For the progressive wave on the wire, state the difference, if any, in the amplitude of the oscillations. Well, there won't be any difference because it's a progressive wave, so everything's going to be moving up to amplitude. So it's just, do you say just state the difference? So we can say no difference. There we go. We don't have to give any kind of explanation. So we like that sort of thing. That's done that. C, describe the difference between the displacement and the amplitude of the wave. Right, well, we've been through this so many times, so I won't write it all out. I'll just say it again. Displacement is the distance from equilibrium point for a point on the wave at some time, and the amplitude is the maximum displacement. So that's that. Describe how a stationary wave is different from a progressive wave. Right, so progressive wave, well, we can say that transfers energy. This is one, I mean, it's just, it doesn't have to have everything written into this, every single difference between them. We just need a difference between them. So the progressive wave transfers energy. A stationary wave, that traps energy in pockets. So traps energy in pockets. Now, if I recall correctly, there's a second part to this question on the next slide, rather than this being the end of it, because I think we do it again with a stationary wave. Yeah, here we go. Figure 5.2 shows the wire of figure 5.1 under tension fixed at points x is 0 and x is 0.6 meters. So that was the wavelength of the previous wave, wasn't it? Frequency of the mechanical oscillator close to one end is varied, so a stationary wave is set up. Right, so they've set up a stationary wave. By considering the motion of progressive waves on the wire, explain how the stationary wave is produced. Right, again, I'm not going to write all this out because I've done this quite a lot. But remember, we've got these 3 steps. So we want to say the incident wave, I'm just going to put key words here, incident wave reflected from the fixed points. So that's the first thing that you want to say on the wire. So the incidence wave is reflected from the fixed points on the ends of the wire. Then we need to say that the reflected wave superposes with the incident wave, and then that this produces a stationary wave with nodes and antinodes. Nodes, antinodes. So, I mean, you probably get sick to death of writing that out by the time you've done all your revision, but, you know, you need to keep going through it, I suppose. Right, in figure 5.3, the solid line of the graph represents a displacement y against position x of the stationary wave. Right, so they've given a solid line at time t is 0, and then they've given a dotted line at 0.75 milliseconds later, once it's flipped over to be, I suppose, anti-phase to that. For the stationary wave on the wire, state the difference, if any, in amplitude of the oscillations R and S. Right, so we've got R and S here and here. Right, so now these are fixed between, you know, inside this envelope of the solid line and the dotted line. You know, R can't get outside of that envelope, and neither can S. So they've got different amplitudes. So the difference in amplitude that we're going to get is going to be, well, S has got an amplitude of whatever that is. What's that, about 1.7? This is all in millimeters. And then R, well, that's easier. That's just going up to 1. So that is 0.7 millimeters. Mark with an X the position of one antinode. Right, well, we've got a couple of antinodes on here. So let's put X up. You want to get it at the top of one of these things. So that's an antinode. So actually, let's put it here. Mark with an X. I don't know. I don't think it would matter whether you put it at the top or at on the axis. It's probably safer to actually put it on the x-axis rather than put it at the top. But I don't think they'd necessarily matter. I mean, the antinode is this sort of vertical line going through that point. So, but yeah, I think put it on the x-axis is probably going to be a safer option. I doubt they're going to be that fiddly about it, but you never know with some of these mark schemes. Mark with a Y on the dotted line of figure 5.3 where the point N on the wave is at t equals 0.75. Right, well, they told us the dotted line is where the wave is at 0.75 milliseconds. So N is just moving up and down. It's just staying in this vertical plane here. So at 0.75 milliseconds, it is going to be down here at the corresponding point straight down. So it's going to be here at point N. That's where it's going to be. So yeah, this one you definitely want to mark it on the dotted line. It's not going to be on the x-axis. I think put the antinode on the x-axis, but you want to make sure that you've marked that new position for N on the dotted line. So yeah, that brings another question to an end. They certainly get through a lot of parts in these waves questions, but you can already see that it's pretty repetitive, the stuff that comes up. So if you can get these descriptions, these definitions, there's a lot of definitions: amplitude, displacement, frequency, wavelength, period, phase difference. If you can get all of those definitions nailed, the description of setting up a standing wave, if you've got that nailed, you're going to get a lot of marks for free when you're going into these questions. And the calculations are pretty straightforward as well, particularly you get used to drawing out the stationary waves to see which harmonic you've got and what's going on with the wavelength. But still, there's another two questions.